Good afternoon, everyone. It is an honor to be here today at the 5th International Conference on Trends in Material Science and Innovative Materials. My name is Vaibhav Tarade, and I am delegated to present our research titled TZSI Infused Adaptive Voltage Conditioning via High Precision Vectorial Modulation. This work is a collaborative effort with my co-author Ms. Pooja Paratwar, and we are affiliated with the Department of Electrical Engineering, the Takala Group of Institution, Pune, India. In this work, as we move toward a more sustainable energy future, integration of renewable sources, especially solar power, into the grid has become crucial. However, with this integration comes significant power quality challenges that impacts the stability and reliability of the system. Today, I will discuss how conventional approaches fall short and introduce a novel topology that offers a high precision solution for the power quality enhancement. Throughout this presentation, we will explore the limitation of existing system, the advantages of the proposed architecture, and its impact on the power grid stability. Let's dive in. This is the outline of my presentation. Introduction. Here, we know that the power quality refers to maintaining a stable distortion-free voltage and current supply in the electrical network. With increasing integration of PV system into the power grid, photovoltaic issues have become a major concern due to the intermittent nature of solar energy. So, my research proposes an innovative TZSI architecture to enhance the power quality to make and renewable energy integration more sustainable and reliable. As the conventional VSI and DVR has their limitation, like VSI has a low voltage gain, poor fault performance, limited fault ride through capability, high harmonics, poor reactive power support, low efficiency, and the DVR has also some limitations like limited compensation range, high power consumption, slow dynamic response, complex control strategies, and bulky and costly. So these are the limitations. So to rid of it, we need to implement or we have to work on new technology or new methodology for that purpose. So it is necessary to implement our uh, TZSI with the high precision vectorial modulation. This proposed TZSI is needed. This TZSI has its advantages. That is the high voltage gain, enhance power quality, fast dynamic response, optimize control, and improved efficiency. Motivation and research objectives. Here, TZSI has its own advantages. That is the dual mode conversion capability, reduced passive components, extended voltage amplification range, and minimize voltage stress on switching devices. I have three motivation points behind this research work. That is the power quality issues, limitation of conventional VSI and DVR, and third one is the increasing PV penetration. Research objectives to develop an innovative TZSI DVR topology for enhance the power quality. Next, integrate high precision vectorial modulation for optimized performance. Next one is to improve the voltage gain and dynamic response without extra boost converters. And next one is reduce harmonics and switching losses for clear power supply. And last one is that enhance the fault ride through capability to mitigate the grid disturbances. This is the control architecture with an optimal constant boost control approach using the unit vector framework. This flowchart shows the process of power quality enhancement in the TZSI DVR. where the process initialization starts with the PV generation, that is the DC power generation from the solar system. It will further goes to the VSI section where a transformation from DC to AC take place. Then it proceed further in the detection of the power quality parameters. If the power quality parameters disturb, if it is detected as no, then this power is will be integrated with the system or grid integration will be done. If the power quality disturbance occurs, then if yes, then proceed. It will be proceed to the TZSI adjustment. In the TZSI adjustment, it adjusts the boost factor to mitigate the disturbances, and this calculations enables the system to boost potential and maintain the power quality. This inverter output is synchronized with the grid parameters, so monitor if the system maintain the power quality parameters. Again, if yes, it will be stabilized. If not, then it will be it should have to be corrected. And the other end of the grid integration, there also the checking of power quality parameters. If the power quality parameters uh, is okay, then it will be continue with the stable operation with the grid integration. If no, then it will be returned to the TZSI for the adjustment and recalibrations. So finally, the system continues to monitor and operate while maintaining the power quality. Now let us see the TZSI operation. Here in the TZSI, it is an refined instance of a classic ZSI which developed to confront the shortcomings of the both classic voltage source inverters and the original ZSI. Traditional ZSI still has a limitations, and TZSI addresses these issues by modifying the traditional ZSI network. So here in figure 3a, it shows the structural visualization of the TZSI in the DC link perspective. In this setup, the DC link potential VDC is there. It is applied to establish the relationship between the inverter's input and responses, where DC link voltage can be the summation of the VL1 and the VC1, the voltage across C1 and potential across the L1. So here during the transition, the diode D alternates between the conducting and blocking stage depending on the direction of energy flow, which where inductor voltage and current indicate the dynamics of the energy interaction between the impedance network layout and the inverter. Here in the figure B, 3B, it gives the TZSI equivalent circuit with the transition. In this mode, the TZSI transmissions between shoot through and non shoot through regimes or states, where energy is stored in the inductors, that is the L1 and L2 here in the inductors. So and capacitors C1 and C2, which are the dynamically exchanged. This transition state balance the energy, and the inductor voltages VL1, VL2, as well as the capacitor voltages VC1 and VC2 with inductor and capacitor satisfying conditions are given in the paper in equation number 4 and 5. And in this state, where in current bypass state shoot through, that is the ST, in TZSI, where single or multiple inverter legs are deliberately short circuited. In this state, boost voltage is increased and accumulate the energy in the impedance source network. During this uh, ST, that is the short through zero regime or state, The source inverters store the energy in the inductors by short circuiting the inverter legs deliberately, and the voltage across the capacitors, that is the VC1, helps to boosting the direct current interconnection potential, while the diode D, here is a diode D, so this remains in the suppression regime or the state. Okay. Now next is the 3C. So in this 3C, TZSI in the shoot through zero regime is shown, in this state is shown, where all the switches in the one section of the inverter are engaged at the same time. In this state, boost the potential using the impedance source power configuration. The capacitor deliver the charge to the inductor. This will result in the zero potential across the inverter bridge, that is the V inverter. Here, energy is accumulated in the inductors. This accumulated energy is given in the paper by the equation number 6, where in this non-bypass phase in a stereo state, the energy flows out of the unidirectional current and impedance source power configuration to the inverter and transfer to the our load. Now here is a last state as shown in the figure 3D. It is an TZSI in the non-shoot through zero regime or zero state, where the inverter operates normally and the impedance sources setup deliver the energy to the load, to our load, uh, and the unidirectional current connection voltage is intensified and applied to the inverter. Now, what is the further outcome? We can see it in next slide. Here equation number 7 shows the intensified DC link voltage applied to the inverter and the current in the inductor and capacitor shown by the equation number 8 and 9, and the shoot through duty cycle, that is the DST, is shown here with a boosting factor, and expressed gain is given by equation number 14 with the modulation index. Here is my MATLAB simulation of my work of TZSI adaptive voltage conditioning configuration. Here MPPT controller, which integrates the incremental conductance algorithm in the conjunction with an integral regulator of dynamically ascertain and sustain the optimal operating point. Here a load voltage and load currents are monitored to detect the disturbance, and reference voltage, uh, that is the ideal voltage for the comparison and the control, is monitored, where the DVR block or restoring block generates the required gate signal for the switches S1 to S6 based on the deviation between the load voltage and standard voltage. Here VSC control block is here. This VSC control block generates the gating signal pulses for the three-level bridge inverter by selecting the right inductor ripple. Here, MPPT actuation system is designed using the conductance increment strategy plus integral regulator technique. The stable operation or stable patterns can be observed if we observe the stable operation or stable waveforms on the scope, then it can be shows it shows that the successful tracking of MPP, that is the maximum power point, by the MPPT computation. This is the voltage converter configuration setting which are applied in my MATLAB simulation. Now let us see the result section. On the screen you can see the simulation outcome waveform, where first waveform shows the grid voltage with the multiple variations and disturbances. Second waveform is the load voltage waveform, which shows the stable output with maintained power quality. Third waveform is injected voltage. This shows necessary injected voltage to maintain the power quality at the load voltage side. Now this is the interpretation of my research work using the graph. First graph shows the efficiency and power loss with respect to the load. At a load 50%, the system operate at higher efficiency. Almost it is 96.5% with the minimal losses of 1.75 kilowatt. When the system is at its 80% load, this is the point of 80% load, and at that time efficiency is slightly decrease at 94.2%, and power losses increases due to the higher current flow. And when the system operates at the 120% of its load condition, this is the 120% load condition, and at that time the efficiency drops significantly up to the 89.8%, and power loss increases drastically, which is almost at the 12.24 kilowatt. Now in the second graph we can see the voltage regulation accuracy, comparing with the other available other voltage power quality maintaining techniques. Here you can see that our proposed TZSI having the 0.5% of capacity or percentage of voltage deviation condition, which shows the highest precision. And from this graph, we can say that our TZSI has an lowest voltage deviation under all conditions. At the THD almost at 10%, TZSI maintain 97.5% precision, where other drops below the 95%. For and also we can say that for the high harmonic condition, that is the THD when it is above the 15%. VS and DVR has 8% and 6.5% sequentially, but the TZSI remains at 5%. So this gives the good performance of our proposed TZSI. Now graph number 3 is there, which shows the total harmonic distortion percentage impact on the voltage precision. So when we consider the precision level, we can conclude or we can observe from this graph is that TZSI maintain highest accuracy compared to other methods, even at high THD level also. And at the 50% of THD, VSI drop 92% accuracy, while TZSI remains at 90%, 95%. So you can see all these values at the graph at this position, and this is the our TZSI graph in red color, and DBR and MSBC perform well but still have higher deviation than TZSI. So from this all interpretation and results, I would like to conclude that our system perform better than other available techniques. Research opportunities. First is the related to the advanced control strategies for the our TZSI network. We can implement our system with the artificial intelligence, machine learning based predictive control, which help us for the dynamic power quality enhancement. Second is the integration with the smart systems. That is the real for the real-time monitoring and control using the IoT-based energy management. It also can help us in the blockchain for a secure decentralized energy trading in the PV sector. Next opportunity is in the hybrid energy system, where we can combine our TZSI DVR with the hybrid renewable sources, which help us with the energy storage integration for to enhance grid stability. And next opportunity is that hardware implementation section. We can develop a scalable prototype for the real world validation. So we can say that the TZSI DVR approach opens doors for all next generation resilience and intelligence and efficient power system. These are the references, and finally, I sincerely thank you all for your time and attention. I look forward to your valuable questions, insights, and discussions. Thank you.